Right, so we're doing another drop test here. We'll be dropping a 2 mass, a distance of 10 centimetres onto a spring. We'll be dropping a 1 mass, twice that distance, 20 centimetres onto a spring, and then dropping a 1 mass 4 times the distance, which is 40 centimetres onto a spring, filming all the compressions. So in terms of kinetic energy and MGH, the 1 mass at 2 heights would be the same energy of the 2 mass at 1 height. So the MGH equation would show that it's the same energy, and the kinetic energy equation would show that these are the same energy. The momentums obviously would be different. In the case of the 2 mass at 1 height and the 1 mass at 4 heights, the momentums would be the same, but the MGH formula and the kinetic energy formula would say that they're twice the energy. Obviously, the compression wouldn't be twice as much because we've only got twice the energy. If we wanted double compression, we would need 4 times the energy, and we've only got twice the energy. So you could argue that, oh, it's not compressing the spring twice as much, but you know, that's in line with everything. It shouldn't do that because we've only got twice the energy. Right, on this video I will upload some footage of the setup. You can see that on the setup I couldn't actually see what the compressions were because the phone holder was actually in the way, but I was that confident that nature does what it does. I didn't need to see them. All I needed to do was have the camera activate the slow-mo, film it, and then go through all the results. So I will upload the footage separately because it's filmed the other way, so it'd be ideal viewing on a mobile phone, probably not good on a monitor because it'll probably flip it the other way. But I got some good footage, good results, lighting was good, everything was good, so that's the setup basically. The 2 mass compressed, so basically you got the spring uncompressed. I put the 2 mass on and that compressed roughly 1.5 mil. The 1 mass on the spring alone roughly 0.5 mil. So the 2 mass under its own weight compressed the spring roughly 1 millimeter more than the 1 mass did. So that will obviously have to factor into the results because that's the standing weight, and we're just looking at the energy of these two when they're dropped, and obviously this one. So yeah, that's taken into account. So yes, I'll upload the results. I'll do probably 4 or 5 runs of each one, and just upload them, and that's it basically. So just for verifying the weights, that's the 2 mass. That's 49.39 grams. That's with a bit of tape on as well, which is how I used it. So 49.35. So we'll take the tape off and measure just the one. So now we've got just the 1 mass with the marker on, and that weighs 24.7 grams. Yep, 24.7, so that's just 1 mass. So yeah, half exactly would be 24.675, something like that. So we're pretty much bang on half. So 1 mass, 2 mass. Right, so this is just a measurement of the spring uncompressed. Measure it at 74.5 millimeters. Oh. 0.5. I can see. So that's uncompressed length, 74.5. So that's the one mass on the spring, and that measures, I'll just get it on the lip of that washer. So that's 74.1. Alright, now we've got the two mass on. Get that on the washer. And that measures 73 millimeters. So a little bit more compression there for the heavier weight. So this is the setup, everything in a fixed position. Phone in a fixed position, that tape down, light, everything fixed. And this is a two mass dropping from 10 centimeters. So same setup now, we just double the height and we're just dropping a one mass from double the height and filming it in slow-mo. So I've now raised the stop to 4 times higher, so we'll be dropping the one mass now from 4 times as high, which will be the same momentum as the two mass at one height.